What if we rewrite the gas law using actual molecules instead of moles? The goal of this video is to understand how to express the ideal gas law in terms of the number of molecules and what the Boltzmann constant is. So in the past few thermodynamics videos, we've been using the ideal gas law. Pressure times volume equals the number of moles times the gas constant times the temperature in Kelvin. But the thing is, the number of moles are big. They're just bundles of particles. So we can replace this mole count with molecules. The formula to do that is N, so number of moles, equals the number of molecules divided by Avogadro's number. Avogadro's number is 6.022 times 10 to the power of 23. This constant and every other formula like this is on the free cheat sheet in the description. And we can substitute this value for N into the ideal gas law. That's how we use molecules instead of moles. So the ideal gas law becomes N over Avogadro's number, RT. And here's the thing, when you divide R by NA, you get a very important value. This value is so important we give it its own name, K. And you'll see why soon. The new final equation of the ideal gas law, the molecular variant, is NKT. And this constant is called the Boltzmann's constant, spelled like this, named after this guy. And this constant is R over NA, which is the gas constant divided by Avogadro's number. Roughly, you don't need to memorize this at all, 1.38 times 10 to the power of negative 23. This is also on the cheat sheet, and it's measured in joules over Kelvin. So what this number tells you is how much energy per Kelvin each individual particle has. So per 1 Kelvin, how much energy is contained for that particle? This is the ideal gas law in its molecular form, where instead of considering mole count, you consider molecule count. It's the exact same law. Now let's see in action with a problem. We're going to use the new molecular gas law, PV equals NKT, to find the pressure inside a sealed container where the numbers of particles inside this container is unknown. So you have a rigid steel canister and it's filled with exactly 5 times 10 to the power of 23 molecules of hydrogen gas. The volume of the canister itself is 0.004 meters cubed, which is about 4 liters. The temperature inside is 300 Kelvin. The Boltzmann constant is K 1.38 times 10 negative 23. Here's what we're trying to find. The pressure inside the canister. We're going to use our fancy new equation, PV equals NKT. We're going to isolate pressure by dividing V onto the other side. P equals NKT over V. And we know all these values. The number of molecules, 5 times 1023. K is this fat number. The temperature is 300 Kelvin. And the volume is 4 liters, or in meters cubed, 0.004. The answer for the pressure comes out to be 1.55 times 10 to the power of 5 pascals roughly. For reference, this is a bit above the atmospheric pressure.